Hello and welcome. In this video, I'm going to explain how to solve pins for Berger's equation. So, how to use neural network to actually solve a partial differential equation, and which is in this video is going to be Berger's equations. So, Berger equation consists of three terms, I would say. The first term is a spatial term, which is this one, and it is the change of u with in relation with x for the first derivative multiplied by u itself, and this is the value what we are going to, or what we try to actually predict. Another spatial term is the second derivative of u with x, or the diffusion term, and this is going to be multiplied by the viscosity v. The last one is the temporal term, or the time-based term, which is the change of u in relation to t. In usual way, we simply make an actual grid, and using this grid, depending on the scheme we will solve, we will calculate the we will have an initial condition and of course boundary condition, and then we will calculate that based on numerical methods, for example finite difference, or even like explicit, or even finite element, and so on. However, what we're trying to do here, we're trying to solve the Berger's equation using basically neural networks, so PINs, so physics informed neural networks. So how to do this solution, or how to get this solution using neural networks, is basically we will start by importing the needed libraries, which is math, numpy, seaborn, matplotlib collections, tqdm for seeing the progress bar, torch, of course, this is the main library, and we import also the neural network part of torch. So this is the first thing. After that, what we will do is we will define our neural network, and with that we will do is we will have an input size of this neural network, a hidden size, and of course an output size of this neural network. We also define the depth of the neural network, and the activation function in our case is tan h function. For input size, in this case, it should be like x and t. So we're trying to solve the x, and we try to solve t, and which is the time, or this is the input. We know we want to know, we already know the x, we already know the t. What we're trying to solve is the output, which is u, the velocity, and the depth of this neural network is going to be, well, we define it. In this case, we will define it as 4, but you can define it as you want. And the hidden size is the number of neurons in the hidden part of the neural network. So after initializing all of this, we will start building our neural network, and in this case, we will start by first defining the input layer. As you can see here, is the input layer is connected directly with the hidden layer, and after that we will pass it through an activation function. Followed by that, we will start defining the basically hidden layers, which is we will have a loop in which we will define these hidden layers, and the hidden layer input size is going to be hidden size, and the output size is going to be also the output size. After that, we will define again the activation function, and this loop is going to repeat itself depending on the number of hidden layers we want to define. Now, once this happens, what we will do is we will create an output layer, and in this case, we'll take a hidden layer as an input, and the output is going to be, in our case, 1, because we're predicting u only value. So in this case, it's going to be u, so 1 output size, and we will pass this into the dictionary using the collection library, which we import this one. We import it from collection library, and then we pass it into a sequential into the sequential part to create the basically deep neural network. This will be set into a feed-forward neural net, or do we define a feed-forward neural net, and basically this is going to be our neural net that we will use to basically solve the model we want. Now, in here for the neural network, what we will need to do is first, this class will define the whole computational process, and the first thing is what we will do is we will first call a CUDA. We will set the device. Are we going to solve it on CPU or GPU? It's very normal, like this way we will do. And then what we will do is we will define the neural network model. Here we will define it, of course, this neural network, which we will build here, will have an input size of 2, a hidden size of 20, and an output size of 1. The number of hidden layers is 4. So we have 4 hidden layers, and then what we will have is the activation function is tan-h activation function, which is actually we already initialize it here. And what we will do here, after doing this, we will start defining the computational range in that we will compute. For here we have x and t only. We have spatial, which is x, and t is the temporal or the time-based component. So first we will have the step size. We'll define the step size. We define the other step size in time, and then we define the x and time range. So for x, it will be from -1 to 1, and from time it will be from 0 to 1 with a step size of 0.1. So this part of the code is going to do so. And what we will have first, we will define the x as a full grid, and this part of the code is going to make the grid of x as a tensor. Now, after that, what we will do is we will start training the model, and the training process is basically, it's of course we're using neural network, so it is kind of we're trying to converge the network based on minimizing the loss of the predicted value of u. But also what we will need to do is we need to actually add a loss function that describes the physics of the model. So the first thing what we to do so, we need to actually define the boundary layers or the boundary conditions. And here we can see the boundary condition is defined, which is when x equals 0. This is the beginning of the boundary condition. Just to make sure that you understand that we have, in our case, what we have is only x and t. So our domain is actually going to be a line, and here is 1, and here is going to be, I think, -1 or 0, I don't know, depending on the definition. And the initial condition will be a sine wave. So this is going to be the initial condition, and as the solution increased, like this direction is going to be the t, the solution will be converged to more like a step size. This is the general behavior of this Bergers equation. So let's do it in code. And so here is the first end is the boundary condition, which is the start is 0, and the last end is -1, means the final element. Of course, x is from -1 to 1, but -1 refers to not the actual -1, means the last element. is not going from the beginning, but actually going from the last. And here, what we will do is the initial condition. We define, we define initial condition, and later we will populate this one. So here we have tensors that actually defined in our as a training data. Now, after that, what we will do is the X training is going to be all of them concatenated together. Now, after that, we will define the first boundary condition to be 0, the second boundary condition to be also 0, and the initial condition is going to be, sine wave. Basically, this sine wave means that our initial condition will be going from u equals 0 at the both ends here, and equals here also 0, and in between we will have a sine wave. So yeah, so this is just basically doing defining the boundary condition and the initial condition. And here the Y train is going to be also concatenated. So the same we did here, we will do here, which is the boundary condition of our domain. So these U's going to be inserted here, and basically we'll change the shape of the Y train. And we start here for the X, we start loading the X train, X and Y train into the model, and we define the mean square error as our loss function. After that, what we will see here, or in this code, what we will see is we defined two optimization methods. The first one is LPFGS, this one, which is which I think I already searched this name. It's one of the it's called limited memory Broyden-Fletcher Goldfab Shannon something. This optimizer is more strict, is a little bit more accurate compared with the Adam optimizer. So this is why we actually use it here, but we also call Adam optimizer. And the reason we do this, because at the beginning we will optimize using Adam, but after that what we will do is we will switch to the other optimizer for the final part of the training. So here we're here already. So we define two optimizers because we will use two optimizers. And now the loss function, which is the very important part of our work. The first one is we clear both optimizers. We make it 0 grid. We clear the optimization in these values for the optimization. We make sure they are clean. And here we start with predicting the Y value using exactly the model itself. And for the loss data is going to be the mean square error. Of course, this creation we already defined it in here between the Y predicted and the Y train. And this is U going to be the predicted value for the whole X, for the whole grid. So this one is actually taking 1 point and predicting this point, but we're actually calculating the whole grid using our model. So it's not 1 point of the whole grid that we defined before. So after that, we will calculate using torch.autograde, grade.grid. This way, we will calculate du of dx, which is the change of u with other tensors, or usual non-scalar tensors. This method we will put, but basically we will calculate the u dx after calculating the whole thing. and we will put du over dt as the first element of the whole output, this one, and du dx is going to be, well, this is the second element, this is the first element, and after that we need to calculate the second derivative of x. For that we will pass the derivative here into the first derivative again, so we'll derive again what we already derived, and this way we will calculate du dx x, and here we just pass one thing here to be 0 because we are interested in the first derivative of course the x again, so this is going to be derived again. Now the loss in PDE, and this is where we actually define the model, or we define the change of du with time. We define the actual, we inform the model using the physics of it, is du dt plus u squeeze multiplied u d dx. This is basically the Bergers equation. So du dt plus the value of u, and we multiply it by du dx, and this is the viscosity term, and then this is the second derivative. So basically we just applied Bergers equation into our model. So once we do that, we use the loss of PDE and we added it to the loss of the data itself, and which is the mean square error, this way, of between the u created and the u calculated. And then we do back propagation, and basically we will every 100 steps we will compute the loss, and just iteration will increase in one value, and then we'll return the loss, will show us the loss. And now is the training part of the data, which is basically we'll have the model and we train it, and I will be in range from 0 basically to 1000. We will use Adam. After that we will continue with the optimizer itself. We will optimize using this optimizer, and of course evaluation, we have model.evaluate, as simple as this. And here we define the network to be this, and of course .net, this class will, we will create this class, and then this class will transform all these values to the other class, which is the neural network. And of course we will train it, and you can see how the loss keep reducing, and until 5000 steps, which we define it here, maximum. No, this is the maximum iteration. I think we should already the until allowable value. Yeah, until the allowable value is reached, the allowable error value is reached. Yeah, tolerance gradient is this much. Until this much is reached, we will basically stop the training process. And after that, what we will do is, well, we evaluate, and this is the fun part of this whole thing. So model.evaluate, this model, net.model.evaluate, and we can see that we just put the each step size, we create our grid in X, we create our grid in T from 0 to 1 with this much difference, and here the X is from -1 to 1, and this is the step size of H. And then we will just of course this is creating all the model as we did before, and then we will pass this X to the model. So this is the model, if it already trained model, and here we will predict these values for the whole X, for the whole gradient, and later we will plot them. So the whole thing is going to be in Y predict, this matrix, and then we just simply do the heat map. for the whole solution. So just to run it, we can of course shift enter. You can see how fast is the whole thing ran. Actually, the plotting took more time rather than the computation itself. This is the beauty of using Bergers. Of course, this is the result, and we start here. The result is a sine wave, so we have it like this. And as the solution start converging, what we will have is it will have a step size kind of solution. So basically, this is how we apply bins or solve bins using Torch.